Okay, good evening everyone, and this is the lecture in which I will cover the second part of the material for this week, the material from 11.2. Can someone confirm that you can hear me? Okay, you can hear me, so all is well. I'm going to get straight into the lecture. You would have seen the announcement that I posted, so please do have a look at the recorded lecture which I posted, the MP4. It's a video, so have a look at it. I know that the writing isn't 100% clear, and I've got some ideas for making it better for the videos to come. So the recording is in the folder for this week. It's in week 2. It is called something like lecture 2 part 2, right? Download it and then see if you can play it on your laptop or on a phone. I'm not quite sure. I think it should play on both phones and computers. So definitely try it out and let me know whether it works for you. What I'm going to do is I'm going to create a discussion forum this evening. And if you've got any comments on the video, please let me know there. Okay, so as I said, I've got some ideas for making the text show up. It's in Blackboard. It's in week 2 in the folder for week 2, Mr. Wu. So please have a look at it there. WebWork has not been opened. I'm still working on it. Remember that the proper one, the one that counts for marks, will only open on Monday morning. Okay. Mr. Wu, I know that I promised to post some the photocopies. I'm still going to get to it. So, okay, let us get on to the actual material. Okay, so in the first lecture, we went as far as example 6, I think. Full screen mode. I think we completed example 6. So if I'm correct, we will start from example 7. We are supposed to start from example 7 in this lecture, right? Yes, we completed example 6. And so now we are on to example 7. There you can see the statement. Find the sum of the series, the sum from 0 to infinity of x to the n, where the absolute value of x is less than 1. Now, notice that this particular series is slightly different from the ones that you've seen up to now, in the sense that the index starts from 0 and not 1. So all of the other series, you started from, the sum went from n equals 1 to infinity. This one is n equals 0 to infinity. And so because it's n equals 0, our first term will be x to the 0, which is equal to 1. Now, a slight technicality here. Notice that if x is 0, then it satisfies the condition that the absolute value of x is less than 1. And so we will, for this example, use the convention that x to the 0 is 1, even if x is 0. That's just a simple convention to avoid us having to treat x equal to 0 as a special case. Okay. Okay, so now let's expand what we have as the series. The series n equals the sum n equals 0 to infinity of x to the n is equal to, if we expand that, remember that x to the 0 is 1 and x to the 1 is x and x squared and so on. So on the left hand side, what's there is 1 plus x squared plus x cubed plus x to the 4 and so on. So if you look at that, then you should immediately spot that this is in fact a geometric series. And for this particular geometric series, we've got a, the first term in the series, being equal to 1, and that common ratio equal to x. Okay, I'll finish the example, then I'll have a look at the comments coming in. R equals x. Now, the absolute value of r is the absolute value of x, which is less than 1. We've assumed that. Okay, and so since that is the case, we know from the material that we covered in Tuesday's lecture, we know that this particular infinite series must therefore converge, because it's a geometric series for which the absolute value of r is less than 1. Right? It's one of the theorems we discussed. And since we know it converges, we also know that that formula 4 gives us a way for calculating its sum. And so the sum from 0 to infinity of x to the n is simply equal to 1 divided by, remember what the formula said. The formula said it's a in the numerator divided by 1 minus the common ratio. In this case, a is 1 and the common ratio is x. Okay, and that's example 7. So I'm going to stop sharing for a minute and just see what the comments are that are coming in. This lecture is a bit less rushed than the ones before. Okay, cool. There's no link or video under week 2 though. So I'll see if I can load it again. I tried downloading it, it's not working. Okay, it's not opening. Okay, I'll have a look at that. I'll post some announcements around it. Okay, thanks for checking. Let's go and continue. That is in fact why I decided to have the lecture as well, because things hardly ever work the way you expect them to the first time round. So now we have the lecture. You wouldn't have missed anything. Okay, so we'll keep doing this until the video recording thing works perfectly. Okay, next example. Show that the series, the sum from 1 to infinity of 1 divided by n times n plus 1 is convergent, and find its sum. All right, so we have to show that this particular series converges and then find its sum. Now, the first thing to spot is that this isn't a geometric series. Right? We'll write out a few terms in a minute or in a few seconds, and you'll see that the pattern is not the same as a geometric series. But we will be able to find a different pattern in it that allows us to simplify the nth partial sum. Remember that Sn was the nth partial sum. So now, if we look at its expansion, this is what it looks like when we plug in values for I. So when I is equal to 1, we get 1 divided by 1 times 2. And when I is equal to 2, we get 1 divided by 2 times 3. 1 divided by 3 times 4, and so on. And the nth term, remember, Sn is the nth partial sum, so it's the sum up to n terms. And so when we stop at n, we get 1 divided by n times n plus 1, right? And so we simplify this expression by using the partial fraction decomposition. And you will remember this technique as something we used in our integration work in the 1A module last year, right? It was 7.4 when we needed to integrate rational functions. And so the partial fraction decomposition of 1 divided by I times I plus 1 is 1 divided by I minus 1 divided by I plus 1. And you can double check that that works by going from the right to the left, right? And now using that gives us a way for getting a handle on the problem, because now this Sn, the sum up to n terms, sum from 1 to n of 1 divided by I plus I times I plus 1, is the sum. We can split it, and now we can write it out like this. When we plug in the values for I, this is what happens. We get 1 minus a half plus a half minus a third plus a third minus a quarter plus, and so on. And that pattern will continue. And the very last term will be 1 divided by n minus 1 divided by n plus 1. And so now you can see what's going to happen. If we regroup, we'll see that I haven't explicitly done it, but by now you can spot it. The negative a half will add to the plus a half to give 0. The negative a third will add to the plus a third to give 0. The negative a quarter, and so on. And so the term, the bracket just preceding the last bracket, will have a negative 1 over n. And so what remains when we do all of that simplification is the expression 1 minus 1 divided by n plus 1. And now we can take the limit as n goes to infinity of Sn, and it is equal to the limit as n goes to infinity of 1 minus 1 divided by n plus 1. And we are free to use the limit laws here. We haven't put that detail in because it's simple, and we get 1 minus 0, which is 1. Now I remind you that the reason we take that limit, the limit as n goes to infinity of Sn, is because that limit is the definition of the sum of the infinite series, right? That's exactly why we do it, because by definition, that is what we mean by that infinite sum. Okay. And so therefore, we've proved that the given series is convergent and that its limit, or that its infinite sum, is in fact equal to 1. Now, one more thing to emphasize, where we say, therefore, the given series is convergent, what we mean is that that calculation, the one that the last step, gives us a number. So the limit as n goes to infinity of Sn results in a number, a real number. It doesn't go to infinity, right? And it's not a case that the limit does not exist. If those were what happened, if either of those two things were what happened, then we would have said that the limit does not exist and that the series doesn't converge. Okay, next example, example 9. Show that the harmonic series, the sum from 1 to infinity of 1 divided by n, is equal to 1 plus a half plus a third plus a quarter, and so on. That infinite series is divergent. Okay, so this is a very important example for a number of reasons. One of those reasons is it's going to be just like the geometric series. It's going to be one of the ongoing examples in the rest of the module. So you'll see that we will be able to show that other series diverge because we can compare them to this series, right? And so it's important that you understand that this is a divergent series. It's also important because it's going to give us a counterexample of one of of one of the theorems that we do it's going to give us a counterexample to show that the converse of a theorem does not hold in general. Okay. It is a little bit counterintuitive. So what I mean by that is when you look at it at first, you would actually expect it to be a convergent series. But in fact, it's not. It diverges. Okay? And we're going to prove that it diverges in this example. And at the end, there's going to be a little bit of work left for you to convince yourself that it does diverge. So I'm not going to spoil all your fun. I'm going to leave some of the thinking for you to do. Okay, so let's see how we go. Now, the way we're going to do this, the way we're going to show that the series diverges is we're going to look at certain partial sums. We're not going to look at all of them. We're not going to look at S1. We're not going to look at S3 and so on. We want to specifically, we'll base our argument on S2, S4, S8, S16, S32, and so on. The last one we'll do is S64. Now, if you look at those particular numbers, you should spot that they are all powers of 2, right? So S2, 2 to the 1, S4, 2 squared, S8, 2 cubed, and so on. And we will use these partial sums to show that the partial sums become as large as we need them to be, right? So let's look at the first one. S2, the sum up to 2 terms, is 1 plus a half. S4, the sum up to 4 terms, the partial sum up to 4 terms, is 1 plus a half plus a third plus a quarter. Now what I'm going to do is, what I'm doing in the last step is, I replace the third with a quarter. Now the quarter is smaller than a third, right? And so the last line must represent a number that's smaller than the one above it. And so we've shown that S4 is larger than 1 plus 2 divided by 2. Right? S8 is the next step. So what you see on the screen now is simply S8 written out in its detail. S8 is 1 plus a half plus a third plus a quarter and so on. And I'm grouping terms again. So I'm grouping the third and the quarter. And I'm grouping all of the other ones coming after that. And now I'm going to use the same thing, the same way of reasoning. I'm going to replace the third with a quarter in the first parentheses, the first brackets. And in the second, I'm going to replace everything, every denominator which is not an 8, I'm going to replace with an 8. And because I do that, I'm using smaller numbers, right? And so this must be true. S8 must be larger than that new number where I've replaced as I explained. And so S8 is larger than 1 plus 3 over 2. And now notice the 3 and the 8. The relationship between them is 2 to the 3 is 8. We do the same thing for 16. So 16 is 1 plus a half plus a third plus and so on, all the way up to 1 over 16. And now I'm going to do the same thing. S16 must be larger than 1 plus a half plus a quarter plus the next set I replace with eighths and then with 1 over 16. And that gives me that S16 is greater than 1 plus 4 divided by 2. And the 4 comes from 2 to the 4. And now what I've shown is I can show in general that S32, well, I can show S32 is greater than 1 plus 5 over 2. And the 5, the relationship here is 32 is 2 to the 5. 64 is 2 to the 6. And so in general, S2 to the n is larger than 1 plus n divided by 2. And this shows that S2 to the n becomes unbounded as n becomes unbounded. And so Sn is divergent. And therefore the harmonic series diverges. Now there are other proofs that the harmonic series diverges. Okay, this is the one that we will use. It's the one from your textbook. And you can see there's a little bit of work left. So technically, you should be able to fill in the details. That line that says S2 to the n greater than 1 plus n over 2. The exercise for you is to go and look at the definition. What does it mean to say that a series diverges to infinity? Right? What does it mean to show that a series becomes larger, becomes unbounded as n becomes unbounded? And see if you can write out those details. Okay? Now, one of the things, before we step away from this example, I'm going to mention something quickly, and then a little bit later we'll have a longer discussion about that, the thing that I'm going to mention now. Now, I want you to notice something. I want you to notice, I'm going to go back to where we started. The harmonic series is divergent. Now, I want you to think about the sequence. Remember, we've got our the first week was about sequences. And these were just functions. They had a sequence is a function that maps the set of natural numbers into the set of real numbers, right? It was a function for which the domain was the set of natural numbers. So there were no sums involved. And so you can consider the sequence where the nth term is the term 1 over n. And so the points, the value of that function would be 1, 1/2, 1/3. Notice I'm not adding anything. 1, 1/2, 1/3, 1/4, and so on. Now, that's a sequence. The harmonic series is the series that we get from adding the terms of that sequence. So something that gets confusing with this work is that students confuse the two. If you look at the sequence, that sequence converges. It converges to 0, right? You can prove it to yourself by looking at the definition, the technical mathematical definition of the convergence of a sequence. That sequence converges, but the series does not. So this is important. This is one of the reasons I said to you that this is an important result. We'll come back to it in about a minute. We've got the following theorem, Theorem 6. If we know that a series converges, then the sequence consisting of the component elements, the things that we add to make the series, that sequence must have a limit of 0. So if we know that the series, if we know that the infinite sum converges, then we must know, it must be the case that the limit as n goes to infinity of an is 0. And you can think, and you know, it's something that is, I think, kind of intuitive. It can't really be any other way, right? Okay, now we're going to prove this. We're going to prove it. It's a simple proof. And so we'll start off by saying, let's give ourselves some symbols. So let Sn be the nth partial sum. And we know what we mean by that. We add up the first n terms of the sequence an. So it's a1 plus a2 plus a3 and so on up to an. And now what we do is we notice that we can also consider the sum up to n minus 1 terms, right? So we stop one short. And we can say, okay, if that's the case, then the nth element of the sequence an can be expressed as Sn minus Sn minus 1. Now we've assumed that the series is convergent. So what does that mean? Well, that means that the limit of the partial sums converges, right? That the limit of the partial sums gives some kind of number. So since the series is convergent, we know that the sequence of partial sums is convergent. And so that means we can give that thing a name. That limit, we can give it a name, we can call it S. But notice that if n minus 1, if n goes to infinity, then n minus 1 goes to infinity as well. Right? If n is a number that grows without bound, then n minus 1 grows without bound as well. And these two, the Sn and Sn minus 1, they're really kind of the same sequence, right? They're just out of step by 1. So to get Sn from Sn minus 1, I simply have to add the nth term of A. And so we must have the limit as n goes to infinity of Sn minus 1 must be S as well. And so therefore, the limit as n goes to infinity of an is the limit as n goes to infinity of Sn minus Sn minus 1. We established that we could write an like that earlier, which is the limit as n goes to infinity of Sn minus the limit as n goes to infinity of Sn minus 1. But both of those limits are equal to S. And so we get S minus S, which is 0. And we've shown that the limit as n goes to infinity of an must be 0. Right. So there we've proved theorem 6. Now, the next bit is not in your textbook. So this is a kind of additional thing that I put in the notes where I think we need to emphasize certain things. And this particular one is important because I think a lot of misunderstanding around the work occurs because of what I'm going to mention next. So now notice that if we have a series, sum of an, say, we always have two sequences associated with that series. The first one is the sequence of its original terms. In other words, the terms that we add. Okay? And the second one is Sn, the sequence of partial sums of the original terms. And confusion occurs because we confuse these two sequences. And now notice that theorem 6 above says that if the series converges, then the sequence must converge to 0. Not only must the sequence converge, but it must converge to 0. So it doesn't work if the sequence converges to, let's say, 10. Because if that happens, if you think about it, then you're still adding an infinite number of 10s, right? It can't work. The points of the sequence must get closer and closer to 0. the sequence, the original sequence AN, must converge to 0. Okay, now let's look at the converse. So again, I'm going to remind you that if we have an implication, a conditional, we called it in Maths 1A in the logic module, in the logic part of the module, we had a statement like A implies B, and we called that a conditional. And we had for a conditional, for the conditional A implies B, the conditional B implies A was the converse of the first one. And so the converse of theorem 6 is in general not true. So what we're trying to say is the fact that the limit as n goes to infinity of an equals 0 is not going to be enough for us to conclude that the series converges. And this is exactly why the harmonic series is such an important example, because it is the counterexample to show that the converse of theorem 6 is not true. How? Well, the harmonic series is a case where we've got the limit as n goes to infinity of an is 0, and yet the series itself doesn't converge. So these things are very, very, they are technically subtle. You need to go and look at them and understand them carefully, right? And there we go. Notice that the limit as n goes to infinity, and there's an infinity missing there. I must fix. The limit as n goes to infinity of 1 over n is 0, but the series does not converge. Okay, now again, I'm going to take you back to your logic module in 1A, where we spoke about again, let's look at the conditional A implies B. And for that conditional A implies B, we said we had this thing called the contrapositive of such conditional. And the contrapositive was the negation of B implies the negation of A, right? And you will remember you did some truth tables to prove to yourself that the truth value of a conditional A implies B is always the same as the truth value of its contrapositive, right? Making them logically equivalent statements. If the one is true, the other one is true. If the one is false, the other one is false. And so theorem 6 gives us what we call a test for divergence. It says the following. If the limit as n goes to infinity of an does not exist, or if the limit as n goes to infinity of an is not 0, then the series, the sum from 1 to infinity, is divergent. And if you go and look at this test for divergence, you'll see that it's the contrapositive of theorem 6. Let's look at an example. In example 10, we are asked to show that the series, the sum from 1 to infinity of n squared divided by 5, n squared plus 4, diverges. And so here we go. And what we're going to do is we're going to calculate the limit of the nth term of this series. Remember, the thing that must, the test for divergence is based on the convergence of the nth term. It's not the convergence of the partial sums. And so we calculate that. The limit as n goes to infinity of an is the limit as n goes to infinity of n squared divided by 5n squared plus 4. And we can use the technique I showed you last week's lecture. The limit as n goes to infinity. We can divide numerator and denominator by the highest power in the denominator. And so I divide the numerator by n squared and the denominator, and I get 1 divided by 5 plus 4 divided by n squared. And that limit is a fifth, which is not equal to 0. Hence, according to the test for divergence, the series diverges. Another note. Now, another technical, very subtle technical point here. Suppose we've got a series, the sum of an. Suppose that we find that the limit as n goes to infinity of an is not equal to 0. And using the test for divergence, we know that the sum of an is divergent. Now, let's consider something else. Suppose that we find that the limit as n goes to infinity of an is 0. Now, this is different now, right? Now we know that the limit as n goes to infinity of an is 0. The question is, what can we conclude about the divergence or convergence of the series in that case? Right? Well, in that case, we know nothing about the convergence or divergence of the series. Absolutely nothing. The series could converge, the series could diverge. Remember that the implication goes the other way. Right? Wanting to say that because we know the limit as n goes to infinity of an is 0 means the series must converge is making the mistake you would have made with the harmonic series. Okay. We've got another theorem that tells us how we can combine series. So suppose we've got series, the series an and the series bn, the sum of an and the sum of bn. If they are both convergent, and if c is a real number, then the sum of c times an converges as well. And to get its sum, we simply multiply c by the sum of an, the infinite sum, that limit. Right? If the sum of an and the sum of bn are both convergent series, then the sum of an plus bn, that also converges, and to get its sum, we simply sum the two infinite sums we had before. And a similar expression for when we take the difference between the two sequences, an and bn, and an minus bn. And as an illustrative proof, we'll do the middle one. We'll prove the addition one. So if the sum of an and the sum of bn are convergent series, then so is the sum of an plus bn, and the sum from 1 to infinity of an plus bn is the sum from 1 to infinity of an plus the sum from 1 to infinity of bn. And to prove it, we'll give ourselves some symbols. So we set up some partial sums. We let Sn denote the partial sum of the ai, and Tn denote the partial sum of the bi. Similarly, both of these converge, right? And so we can have a sum S for the infinite sum of the A, and T for the infinite sum of the B. Right? We can do that because we know that they converge. We're assuming that they converge. And so now we can set up a new partial sum for the sum of the sequences. So we've got a new sequence now. An plus Bn is a new sequence. And so it needs a new partial sum. So let's call it Un. Un is the sum from 1 to n of ai plus bi. We use one of our equations that we developed in that chapter 5. We get the limit as n goes to infinity of un is the limit as n goes to infinity of the sum from 1 to n of ai plus bi, which is the limit as n goes to infinity of the sum from 1 to n of ai, plus the limit as n goes to infinity of bi. Notice this last step, that second equal sign. We can only do that because the individual limits exist. That's a condition that comes from the limit laws, which is equal to the limit as n goes to infinity of Sn. Well, that the sum from 1 to n of ai is Sn, and the sum from 1 to n of bi is Tn, right? That's the symbols we use to represent those sums, the partial sums. And that, of course, is S plus T. Therefore, this new sequence, the sum, this infinite series made from the new sequence is convergent, and its sum is equal to the sum of the original sums. And that's it. Okay, last example. Find the sum of the series, the sum from 1 to infinity, 3 divided by n times n plus 1 divided by 2 to the n. And so look at the second component, look at the second term in the bracket, 1 over 2 to the n. You should immediately spot that as a geometric series with a equals a half and r equals 1 over 2. And so the sum from 1 to infinity of 1 over 2 to the n, I can calculate that, right? Because I know, because r has an absolute value which is less than 1, that series converges. And we've got a theorem that tells us what the sum is. It's the first term divided by 1 minus the common ratio, which gives me a half divided by half, which is 1. Okay. Now the second one should also look familiar, or rather the first one. From example 8, we know that the sum from 1 to infinity of 1 divided by n plus 1 is 1. Now there's simply a 3 on top. So we use one of the laws we just looked at, the one with a C, and we can reason as follows. By theorem 8, we know that the given series is convergent because the two component series are convergent. And so we can say the sum from 1 to infinity of 3 divided by n plus 1, it's 1 over 2 to the n is equal to 3. Sum from 1 to infinity 1 over n plus 1, plus the sum from 1 to infinity of 1 over 2 to the n is 3 times 1 plus 1, which is 4. Last note, quite an important one as well. Suppose we know that a series, from a certain starting point, a series converges, right? And that starting point is not 1. Then surely the fact that that infinite list of terms after that starting point converges means that even if we shift it to 1, it still has to converge. So what I'm saying is, if the sum from 4 to infinity of n divided by n cubed plus 1 converges, then surely the sum from 1 to infinity must converge, because the remaining terms can only result in a finite number, right? So here we've started from n equals 4 and gone down to n equals 1. But it doesn't matter how big that number is. So if we look at in general, if it is known that the series, the sum from n plus 1, capital N plus 1 to infinity converges, then the full series converges as well. Now that capital N can be a really large number. It could be a billion. Doesn't matter, because infinity is much bigger than any number, right? And so if the series converges starting, if I add from a starting point of a billion forward and it converges, then everything below that must also make it converge. Okay, I'm going to stop sharing. We've got about a minute for final comments. I'm going to have a look at what you've said, and then I just want to wrap up with comments about the recording. Why doesn't the divergence, let's start a little bit earlier. May I ask you if sigma 2 divided by n is still a harmonic series? Replacing the denominator as an example. Okay. I just want to start. Is there a way we can identify that a series is harmonic? So to answer that question, Mohosana, that series that you see there is the harmonic series. So the harmonic series is the series that looks like this. The sum n from 1 to infinity of 1 divided by n. Done. There isn't a different harmonic series. So Ms. Leong says, so why are you replacing the denominators in example 9? Because I want to show that S2 to the n is larger than a certain number on the right. Right? So I need a way of introducing the greater than symbol. That's why I'm doing it. That's why I'm replacing the denominators on the right-hand side of the inequality, right, with numbers that are smaller. That's why. Malobola, may I ask if sigma 2n is still a harmonic series? Malobola, technically no, but technically it is 2 times the harmonic series, right? Because that 2 above the n is just a C, right? Does it make sense? I see there, Mohosana, you say, thank you, sir. Does it mean you understand? I hope so. Okay, cool. You say yes, I'm happy. So, Malobola, okay, cool. I'm happy. Now, Mutlwane. So I'm confused. When we check if the series is convergent, we use the sequence of partial sums. Does it mean that we make conclusions based on theorems of sequences? So yes, so here's the relationship. This is a very good question. And I understand why you are confused. Remember, the very first lecture, the work we did last week, was work on sequences. It was a sequence. It had nothing to do with sums. Now, what we did this week was to introduce this concept of an infinite sum. Now, in order for us to define what it meant for this infinite sum to have a real number, for this infinite sum to be meaningful, remember, I said to you, this infinite sum can only be meaningful if it's possible for us to get a number as an answer. If every infinite sum becomes infinite, then there's no point in talking about it. Then it's not a useful concept. Now, we said we are going to define the convergence, this infinite sum, the sum of infinite terms. We are going to define what it means in terms of sequences as follows. For each infinite sum, we define the partial sum up to n terms. And so now Sn, the partial sum up to n terms, that is again a sequence. But it's a different sequence from the one you started with. So that's why I made that the notes. Go look at the notes. I said to you, with each series, we associate 2 sequences. The original sequence, the ANs, then the sequence of partial sums, the SN. You must understand that difference. The limit, the value of the infinite sum is the limit of the second sequence, the sequence of partial sums. Okay. P. Binney says, why doesn't the divergence test work for the harmonic series you showed us? I don't know what you mean, why it doesn't work. The divergence test works perfectly. I don't understand what you mean, Binney. So, sir, in the case of series, we don't consider sequences. I don't understand what you mean by that. What do you mean we don't consider sequences? I just explained to you that for a series to know whether the series converges or diverges, we must look at the partial sum, the sequence of partial sums of the series. If that sequence converges, then the series converges. If that sequence does not converge, then the series does not converge. So actually, your last statement is wrong. So you said, so sir, in the case of series, we don't consider sequences. Yes, we do consider sequences, if I understand your question properly. Go read it again. Okay, go read it again. Make sure what you've asked is probably the most important thing in this course, because it's the one thing that students will confuse. Okay, before you go, those of you who are still here, what I'm going to do is I'm going to remove the file that's there, the recording that's there, because you say it doesn't work. Then I'm going to make a new one or rename it or do something else, post it again, post an announcement. I'm going to create the discussion forum. If anything works or doesn't work, let me know in the discussion forum, because I don't want to get 400 emails. Okay, thank you guys. We'll speak again next week. Go do some maths.